decided to, or we described how we would focus on the transformations of translation, scaling, and rotation. So moving things around in 3 dimensions, maybe scaling them up and down in various ways, and rotating them around in any orientation in 3 dimensions. And these transformations will be important both for picking up basic objects and moving them into the environment and rescaling them and rotating them around, positioning them in order to build up a realistic environment using basic building blocks. So we'll use them for that. So these will act on the kind of objects to pick them up and place them and build the world. They'll also, so I'm going to get some copies of these here. They will also be used for a second task of producing a view of the 3-dimensional environment, right? So, you know, the computer, just take a copy of these guys. The computer doesn't just close the door there, actually, as well. You can't just say to the computer, you know, show a picture of the 3D environment. Well, you can, but the computer goes through many, many steps in order to produce the flat 2-dimensional picture on the screen. And we'll talk in detail about the steps when we get into chapter 6, but it mainly involves, so you've got the 3-dimensional world, which is represented by the vectors and everything in our model, and to produce a picture, you have to specify 2 main things. You think of the screen, or you think of the view being shown to the viewer as that produced by a virtual camera. Okay, and the camera has to be located at some position within the world. So there has to be a viewpoint somewhere in the world, and the camera has to be pointing in a certain direction. So depending on where the camera is located, and depending on what direction the camera is looking in, that will decide, or that will determine the picture that gets shown on the screen. And so the operations of, well, mainly the operation of rotation will be needed to kind of rotate the environment around so that it presents a certain side of itself to the viewer in some sense, okay? So the transformations are used in these 2 different ways, to populate the world with our basic building blocks, rescale them, move them around, rotate them, but also then to manipulate the whole environment in one go, to spin it around, to tilt it, to shift it around so that it presents a certain aspect to this virtual camera that will lead ultimately to the image that's shown on the screen. Okay. So now I'm not going to avoid completely re-giving the lecture again, but we mentioned homogeneous coordinates in 3 dimensions. We looked at the 3-dimensional translation matrix in homogeneous coordinates for 3-dimensional space, which was just leaping up a dimension from the 2-dimensional one. We looked at the scaling matrices, which were again just making the obvious adjustment to the 2-dimensional case. Well, rotations were quite a different thing, because suddenly, so translating in 3 dimensions is, you know, there's nothing more to say about it really than translating in 2 dimensions, and the same with rescaling. Okay, you've got an extra dimension to take account of, but it doesn't really introduce any more complication. But rotations is quite different. In the plane, you're rotating around a point, whereas when you're rotating 3-dimensional space, you're rotating around an axis of rotation, which is a whole line. And suddenly there's in the plane, there's just 2 dimensions in which the line can move around, in which the center of rotation can be located. So there's 2 degrees of freedom for the center of rotation. But for rotation axes in 3 dimensions, there's much more, because, you know, even talking about lines going through a certain point, suddenly, you know, you can be any line pointing in any direction. So there's lots of freedom there. And then the line doesn't necessarily have to go through this point. It could be shifted out to anywhere. There's a lot more room to move around in, well, it sounds trite when you say it, but there's a lot more room to move around in 3 dimensions than there is in 2 dimensions. And that, particularly for rotations, that means it takes a lot more detail to describe them. So how did we approach this? Well, we approached it in general, we're going to have to be able to deal with the rotation axis of this form, which is, so this is the vector equation for any line, for a general line in 3 dimensions. It's a line which goes through a fixed reference point P, and it has a direction vector D. Okay. But we began our discussion with some simpler cases of rotation, and that was just where we rotate around 3 special lines. And without having built up anything, the 3 special lines that there will be in the environment will be the lines that go along the coordinate axes, along the x, y, and z coordinate axes. These are all special lines. They go in those directions, and they're all going through the origin. And these are the rotation matrices for rotating by an angle theta around one of those axes. Because you have to really pin it down what you mean rotating in an anti-clockwise sense by an angle of theta when you look along the relevant axis back towards the origin from a point on the positive side of the axis. To really nail it down and be specific about what transformation you mean, you have to kind of say all of that. Now, we won't be taking up our time by saying that all the time. This will be the conventional way of talking about a rotation. So we will say rotate by theta around the z-axis. And it will be understood that we mean in an anti-clockwise sense when viewed from a positive point in the z-axis looking back towards the origin. Okay, that's the convention we're going to stick with unless we specifically say otherwise. These rotations have names coming from other disciplines: roll, pitch, and yaw. So these are terms used in aeronautics to describe the orientation of an aircraft, and they may even be originally have come from shipping to describe boats. But yaw is rotation around the y-axis. So if you think of the plane heading in the positive z direction, yaw is rotation around the z-axis, so it changes where the plane is going. Roll is the plane rolling from side to side, and pitch is the plane pointing up or down. Okay. And these terms are used when talking about computer graphics sometimes as well. Now, this is where we got to last time. Wasn't it? Yes. So how are we going to rotate around other axes? How are we going to rotate around a general axis? What we want to do is obtain the matrix that can do that. So obtain a matrix such that when we multiply it by any position vector of the point, it will give you the image of that point under rotation around whatever line it is we're talking about and whatever angle. So we'll approach this in a couple of stages. So this is what we finished with last time. So here's a generic line shown in the 3-dimensional space. You got the xz axes representing the ground plane, and then the y-axis is the vertical axis in the environment. So here's a general line. It's not positioned at the origin. It's going through some reference point P, and we'll think about it when you're looking at it that it's not going through the origin. It's kind of up above the origin, up above the xz plane, and it's going in this it's going in that direction D, which is no particular special direction. Okay, and we're going to rotate by some angle around that axis. Well, rather than describe, we're not going to give a general formula which shows you every exact entry in the rotation matrix for that, because I mean you can do that, but the expressions in each of the entries are quite complicated, and it's not so easy to link it back to the geometry of the situation. So the way we're going to approach it is we're going to describe how you rotate around that with a rotation sequence, a sequence of transformations which makes use of just translations and the yaw, pitch, and roll rotations, just the 3 basic kinds of rotation matrices we've already seen, rotating around the x, y, or z axes. And their matrices are fairly easy to understand because they're rotating around the coordinate axes of the system. That means there's lots of zeros in the matrices, and then you just have cosine or sine of the angle. It's quite easy to appreciate where those matrices come from if you draw the simple diagram of rotating something around one of the axes. Okay. So our ingredients to build a general rotation matrix, just want to get the notes in the chair there. The ingredients for building the general rotation matrix will be translations and the 3 types of rotation. Okay. So what we're going to do is first of all we're going to shift the whole space so that the line, the rotation axis, is brought back to the origin. Okay. So you translate everything, all the objects in the space, so that you draw the axis of rotation back to the origin. Okay. So that can be achieved by translating everything by minus p. You can see there. So now we're talking about rotating about a line which goes through the origin. It's got a not particularly special direction vector d, which you have to deal with, but at least now it's a line which goes to the origin, so that's a bit simpler. And then we go through a sequence of rotations which I showed a few extra diagrams last time. I do seem to be going through the whole of last lecture, but it's no harm just to get us up to speed. So we then take the environment and we rotate it with the yaw rotation, rotating around the y-axis to kind of to take the rotation axis to bring it back into the YZ plane. YZ plane. Okay. So you shift the whole thing around. So d, I probably shouldn't still be calling it d. I should probably call it d prime there or something. You know, it's because it's moved d. It's no longer exactly d. Maybe we should call that d prime. Vector d prime. So that's now in the YZ plane, and you then can do a pitch rotation, rotating everything around the x-axis, down or up as appropriate, to bring d prime now, maybe I should call that d double prime. You still think of it as the direction vector, but now it's nice and special and well behaved. It's pointing along the z-axis in the environment. And we want to rotate around that line by some angle. Well, that's just rotating around the z-axis by a certain angle. So it's at this stage that the actual required rotation that was originally asked for is performed. That's when the things move by the angle theta. The other angles that things have been rotated by are angles related to the orientation of the direction vector d, not the amount of rotation that was required at the start. So after you've done RZ theta, after you've brought the rotation axis down to be along the z-axis, you actually do the required rotation. And then you reverse the steps and send everything back to its original positions where it ought to be. So after doing the actual rotation, you then reverse the pitch rotation. So you apply the inverse of this. So this rotation here would have been an Rx rotation, some kind of Rx rotation. You reverse that Rx, you apply Rx inverse. You reverse the yaw rotation, you apply Ry inverse. And finally, you do the inverse translation. You add P back onto everything. And that will send the rotation axis back to where it was originally. So all of the points along the rotation axis at the end of this whole cycle will be back to where they started. Yeah, that's okay, because rotation's about a rotation axis. The points in the axis don't move at all, because they're being rotated around, so they stay stationary. So anything which was on this line here, shown in this diagram to begin with, moves all its way here. By this point, they're on the z-axis, but then you rotate around the z-axis so they don't move, and then you just reverse these operations. So they get sent back to where they were at the start. But any point off the axis, when you go down through these operations, they become a point close to this rotation axis. When you go halfway through, and when you get down to this stage, it's a point close to the z-axis. It then gets rotated by theta, and it then gets sent all the way back. And so it's now a point close to the axis d, but it's been rotated by an angle theta around d. Okay. So it seems a lot of trouble to go to describe the rotation. Like, why can't you just do the rotation up in that picture there? Well, the benefit is that the ingredients in it, the translation, yaw rotation, pitch rotation, roll rotation, and so on. Or no, sorry, yeah, yaw, pitch, and roll. And those are what we regard as standard rotations, and their matrices are easy to describe, easy to write down, given the data, and so that's how we'll obtain the general rotation matrix required to perform this rotation, indicated up here. So what we want to do now is actually, let's look in detail, let's describe, let's determine exactly what each of the ingredient transformation matrices will be, so that ultimately you'll be able to implement this on the computer. Okay. So first of all, the first stage, well, that's the easiest one. We start off with the general rotation axis. We want to move it to the origin. So as we've already said, we want to translate by the vector minus p. So the homogeneous coordinate transformation matrix for that translation of three-dimensional space is given there, T. So you just have the negative of each component of the vector P in the fourth column like that. So that moves everything to the origin. Then we want to perform, let me just look at my notes here. Then we want to perform the rotation that's going to bring the rotation axis, that's going to bring it into the YZ plane. Now we can sketch some diagrams to help us here. Okay, so let's do that. Yeah, it's just like this. It's just this diagram here. So here's our X, Z, and Y. And at the moment now, our D is positioned here, and this is a certain height above the XZ plane. And okay, we're going to call that V. And it's this angle we're talking about here. So at this stage, the rotation that we need in step 2, is the one that's going to send D back to the back to here into the YZ plane. So the angle we're talking about is this angle phi here, and it's specified in the notes. Phi is the angle between the side V and the positive sense of the Z axis. Here's the Z axis. Now what is V? V is the vertical projection of the vector D down onto the XZ plane. So that's specified there. So we got the direction vector D, and V is the magnitude or the length. V is the length of this vertical projection of D down onto the XZ plane. So the triangle, as with all these things, if we want to determine the sines and cosines, we need to identify the right angle triangles that are in use. So we're talking about these two lengths, these two sides here. Now this side is length dz, that's the z coordinate of D. This side going across here, so it's this length of this side here, that's dx, that's simply the x coordinate of D. This height here, of course, is dy, that's the y coordinate of D. So what do we want to do? We're rotating about the y-axis. So think of yourself up here at a positive point in the y-axis, looking back down towards the origin. What kind of a rotation are you looking at? You're looking at rotating everything anti-clockwise sense. You think of your eye up here, looking back down here. The rotation you want to do is rotate things onto the YZ plane. So you want to rotate anti-clockwise by the angle phi, by whatever this angle is. Okay. So that's this matrix here. Okay, so this is one of our basic standard axis rotation matrices in 3 dimensions. So it's cosine phi minus sine phi, and cosine phi in the appropriate positions. The first and third columns. And so, for instance, what's cosine of phi? Well, cosine of phi is the adjacent over the hypotenuse. So the adjacent side to the angle phi is this length here, which is dz. So it's dz over v. That's why we see dz over v here, or in your notes. The minus the sine of phi. Well, the sine of phi is opposite over hypotenuse. So its opposite side to phi is this side here, which is dx over v. It's minus sign we need, so that's why it's minus dx over v. Okay. So these entries here are all read from the right angle triangle in the diagram here, featuring this rotation angle phi. Now, if d is specified as part of the setup, then we take that to mean that you're given the components dx, dy, dz. So what's v? I mean, what is v in terms of the data here? Note, so what's v equal to? If ultimately I want to describe everything in terms of just the direction vector d, well, v is the length of this side, which is the hypotenuse to the triangle with sides dx and dv. So v is going to be the square root of dx squared plus dz squared. Okay. So everything in this matrix comes just from the data. The data describing, specifying the original rotation we want to achieve is the data for the rotation axis, which would be the reference point P and this vector D, in addition to whatever the angle theta is. And we don't need the angle theta yet. Here we're just talking about this angle phi, or its cosines and sines, but they're determined by these ratios, or components of D over this other quantity V that comes from the data as well. So, you'll be able to write a MATLAB function which says, give me this rotation Y matrix, and it can give you this matrix. If it's given the components of the direction vector D, it can output this matrix. So it can calculate everything. Okay. So after having done that, what does the picture look like? So you perform this rotation Ry, then we'll just focus on the Y and the Z axis. Here is our vector. Now let's call it D prime, different vector. But what kind of components does it have? So if you look at the original picture, rotate the thing round so it looks in. It's this length here is V, and this height will still be the height dy, won't it? So just be careful. The length here at this side is not dz. Okay, this would be the length dz if we just projected d onto the yz plane. But that changes the length of d. So we're not projecting d onto the yz plane. We're rotating it around. So it's this length here. It's this length v, which after you've rotated around is the length running along z, and which goes to underneath the tip of the vector z, of the vector d. So there's this picture, and here now there's going to be an angle psi, Greek letter psi. How should we be writing that? Yeah, actually it should probably be looking more like that. Greek letter psi. Theta, phi, and psi, these letters that are traditionally used to denote angles. So what's required now? Remember, we're trying to get the rotation axis onto the z-axis. So you can see what needs to be done. We need to rotate things by this angle, well, by minus phi angle. The x-axis at the moment, where's the x-axis? The x-axis is coming out towards you. So you are all at a positive point. Well, you're all on the positive x half of the space. The negative half is behind the screen. So you're all at the positive half of the space on the positive x-axis, and you're looking back. You're all looking back towards the origin, so you can all see we need to rotate by. Well, we need to rotate by the angle psi in a clockwise direction. So we normally talk about rotations anti-clockwise, so we said we want to rotate by the angle minus psi. Yeah. If you rotate it by psi, you bring it back up this way. If you want to rotate down through psi in a clockwise direction, that's the way the clock goes. So you want to rotate anti-clockwise by minus psi. So that's this rotation matrix Rx there. The subscripts are a bit small. They're a bit too small for the screen here, or the resolution on the printout. This is Rx, you can see in your notes. This is the rotation matrix by an angle minus psi. And can you obtain these sines and cosines just from the data? Well, yeah, because they're just sines and cosines of this angle, so they're going to be the appropriate ratio, either v over, well, what's that length of that magnitude? The magnitude of this vector d prime, note that the magnitude of this vector d prime is the same as the magnitude of the original d. Where did you get this d prime from? You got it from the original vector d by translating it. Well, translating it doesn't change the vector at all. Then you rotated the vector around. Well, that doesn't change that's an isometry. It doesn't change the length of the vector. So this vector still has length, magnitude of d, which ultimately is determined in terms of the data of the problem, the original components, square root of the sum of the squares of the original components. So you can easily write down the sine and cosine of psi as either v over this or z over this. So I set it up here. I was using d. I was using just a normal scalar variable d to refer to this magnitude, and that's the d you're seeing in the expression for the matrix here. Okay, so again, appreciate that the matrix you need, it's completely specified in terms of the data of the original setup, the original ask for rotation. So now you're having done that Rx, then you're now in this situation. So you've now got this vector d double prime, which is the rotation axis we want to rotate around, and it's now pointing exactly along the z-axis. So finally now we can actually carry out the rotation by the angle theta that was originally asked for. And that's now a rotation matrix Rz. You can see in your notes. And we're going to, so this is the form of an Rz matrix, just inputs the angle theta that was supplied originally, and that carries out the rotation. Okay. But then you want to roll everything back to send everything back to its original position that you want it to be in. So when you're performing Rz theta, and then you want to roll everything back. So you want to go back up this way, which is doing Rx inverse, and you go back up this way, which is doing Ry inverse. And then finally, you'll want to do the translation inverse. It's the translation which got us into this step here. We had to translate first to get the rotation axis to be through the origin. Then we rotated y, rotated x, rotate z theta, rotate x inverse, rotate y inverse, and finally translate inverse. So this thing is called a rotation sequence. It's in some ways it looks like a complicated way to carry out a rotation, but it's worth it because the individual steps are very standard. Just translation or rotations about one of the three special coordinate axes. And it's called the yaw, pitch, roll rotation sequence, because that's the order in which the original rotations are applied, yaw, pitch, roll. There's nothing God-given or unique about it. You could achieve a similar output by choosing different orders to do the rotations in. But it's kind of settled upon as, you know, it's like everybody agreeing to drive on the same side of the road. You may as well, mostly everybody do things in the same way. So it's a traditional, conventional sequence of rotations to use. There's nothing special about the z-axis. You could have just originally said, well, ultimately we want to rotate around the y-axis, so we want to rotate everything. So D points along the y-axis, then rotate around the y-axis, and then undo everything. But, well, yeah, you could do it that way, but you wouldn't be doing it the same way that most people do it. So, okay. So these are our individual matrices. So now in the course of your program, it doesn't mean you have to separately multiply the vector by each of those matrices and then do the next thing. You just can form the overall rotation matrix. Because remember, composing operations, the matrix for a composition of operations is just the product of the individual transformation matrices in the correct order, in the right order, and in the faithful order which matches the order in which we're doing the operations. So the order in which we do the operations is T first, then Ry, then Rx, then Rz, then Rx inverse, Ry inverse, T inverse. Now don't lose it all at the end by writing those orders down from left to right, of course. Remember, we use our matrices by multiplying the column vector of the argument with the matrix on the left. So the first thing that gets applied goes on the right of the matrix product. And then you work back. This thing is this thing that's done last. So first you do T, then Ry, then Rx. This is the Rz theta. That's the one which is actually doing the rotation by theta. This was all just the setup to get the rotation axis on the z-axis. So actually it's, yeah, you could even put a subscript theta there or something. Then you're undoing this Rx, you're undoing this Ry, and you're undoing translation. Okay, so it's a product of those seven transformation matrices. Tell him why he's, what's his error. So Alex said, doesn't this all cancel down to Rz? Criticizing somebody in a good, helpful, everybody learning. Yeah, no, that's fine. I'm not being quite, well, let's get you to criticize yourself. What? Yeah, there's an inverse for all the others. Whoa. It isn't commutative. For a moment there, I think you thought it was, didn't you? Because you said, yeah, bring the x with the x inverse. It's not commutative. Excuse me? Yeah. If there's no Rz in between them, yeah, then this is beside its inverse, so identity matrix. Then this is beside its inverse, identity matrix. No need to apologize. That is learning in action. You think something and then you correct yourself. You figure it out. That's brilliant. Well, we haven't gone to that. We haven't gone to that effort to describe the three-dimensional rotations in that way. I mean, you could do it, but it'd just be a lot more involved, because now if you want to take in reflections, you have to reflect in planes now. So you have to, to specify any reflection, you have to specify the plane. To specify any rotation, you have to give the reference point on the axis, the direction of the axis, and the angles. There's 3 bits of information now to rotation. So, I mean, you could do it, but the approach we're taking here is much more focused on the implementation, on getting the computer to do it. So this is something you write a little MATLAB program, which, given the data P, D, and theta, can output the matrix R. Because all you need to write down these matrices, well, you need the formulas for them, but the ingredients that go into the formulas are the components of D, the angle theta, and the translation needs the components of the reference point P on the rotation axis. I would love it if we had loads of questions like Alex's question and lots of discussion and people seeing how things work and, things clicking and realizations. That would be. Well, yeah, we kind of did. We kind of did do that too, in a sense. Let me show you something. Just bringing us chapter 4, but it's good because it shows the same idea at work somewhere back here. Yeah, here was where we were trying to get at the standard form for a general rotation. This was rotating around a rotation center with position vector c by an angle theta. But look what we did. It's a certain translation to bring the center back to the origin. Then it's a kind of a standard simple rotation about the origin, and then you translate back. So this you can see as a kind of baby. Can you rewrite a translation using rotations? Yeah. A general 2D isometry. Well, no, because the description we settled on, where is it? The description we settled on was that any isometry can be written in this form. Some translation after a lambda A. It turned out, after we looked at the classification, that this lambda A was either a rotation or a reflection. So I think what you're gunning towards is some standard way. So 2D isometries will look like this, where here you either have an R or a Q. So you can get any 2D isometry to be a T after R or a T after Q. Yeah? What we've just seen here with the rotation sequence is a way to write any general R. So this R here could be any rotation of three-dimensional space. And it's kind of, well, it's kind of standard form, or its standard way of arriving at this is going to be the rotation sequence. And it's this product of matrices which describes the rotation sequence. First translate, then yaw, pitch, roll, pitch, yaw, and finally translate again. That's the kind of standard description, as we've set it up here, of a general rotation. Yeah. So in a future assignment, when you get onto this virtual environment, you're going to be working with a bit of MATLAB code. Now, whether I get you to write all this from the ground up, or whether I supply some scaffolding here, I'll give you some scaffolding. But, everything's fully specified there. And I've stressed how all the ingredients for these individual things, they all come from the specification of whatever the rotation is, the P, D, and the theta. Okay. And just some more terminology. So these yaw, hold on, flipping over that. Yaw, pitch, and roll. That's terminology to know about. Also, these angles here, these phi, psi, and theta, they're also known as Euler angles. So Euler angles and the yaw, pitch, roll rotation sequence. It's one way of describing rotations. But you see, there's so many choices, there's so many axes around, there's so many orders in which you can do things. You can give a similar formal description of a general rotation using lots of different choices. But we're going to settle on that one to use. And just be aware, if you're reading other sources and in other disciplines away from computer graphics, people do talk about Euler angles still. And they also talk about yaw, pitch, and roll sometimes. But sometimes the meanings can be flipped. So there's no kind of universal, and people use phi, psi, and theta in various different ways. So there's no kind of universal agreement about, there's no unique meaning necessarily to these terms across different disciplines. Within computer graphics, it's pretty standardized. But even there, you have to be careful. So if you're going to any new source and jumping into the middle of it, where they're talking about rotation sequences, you need to identify very clearly how they're setting things up. Okay. No, I think I anticipate, and we'll give you much more information on this, but I anticipate, I keep on flipping the wrong thing. I anticipate that these standard rotation matrices would be in a formula handout. Yeah. But, and like a question might say, use the yaw, pitch, and roll approach to describe this. And I wouldn't necessarily, because, you can look at that and think, oh, that's a silly long formula you have to memorize. Well, it's not. It's more to know the principles behind it. Translate to the origin, rotate to the YZ plane, rotate to the Z plane. That determines what you write down there. Yeah. But no, I'm not requiring you to have kind of photographic memory for all of these things, but a clear understanding of the principles. Yeah. Okay, I'll see you in an hour then. We'll make a start with chapter 6.